Hi everyone, we are group number one, and this is our journey to a cleaner water.
To kick off our sustainable water project, our team gathered to brainstorm a title that reflects our mission on finding effective ways to preserve and reduce water consumption. Meet our team, Group 1, united with one goal to conserve water for a better future.
After convincing our idea for almost 2 weeks to the one and only Dr. Lim, we got the green light, our project title, Purification of Lake Water using Microalgae and Biochar.
With his support, we were also granted permission to use his algae stock for our experiment.
Now it's time to collect our water sample. Some of our team members went to the lake nearby Visit Cafe to get the lake water sample.
With approval secured, we rolled up our sleeves and got to work. Inside Block 20's lab, we built a simple algae cultivation setup using UV light, wiring, and a pump system to keep our algae happy and growing.
Here's our complete algae cultivation setup. Simple, efficient, and ready to grow. Every component plays a role in creating the perfect environment for our algae to thrive.
Next, the preparation of our second medium, Biochar. In this clip, we can see Jingy crush it into smaller pieces to increase its surface area, making it more effective for adsorption.
Once it's ready, Mashi has brought it to the furnace for calcination to enhance its porosity and performance.
Our algae was cultivated for a week. During this period, we carry out UVVs, also known as optical density, at 680 nanometer to monitor its growth and make sure it's growing healthily.
To monitor the growth of our microalgae, Jingy and Ida have performed UV-vis analysis on 3 alternating days. We set the wavelength at 680 nanometers as this is where green algae absorbs light the most. This analysis helps us predict and track algae growth throughout the cultivation period.
The results from our UV-vis analysis showed a noticeable increase in absorbance at 680 nanometer over time, especially by day 7. This indicates that the microalgae successfully grew throughout the cultivation period, confirming healthy biomass development for our purification experiment.
Next testing is dissolved oxygen DO. It shows how much oxygen is available in water, which reflects both cleanliness and how suitable it is for life. Our lake water started at a concentration of 7.73 mg per liter, which was slightly lower than the drinking water benchmark of 8.4 mg per liter.
After algae treatment, DO rose to 8.34 mg per liter, likely due to photosynthesis adding oxygen and nutrient removal, reducing microbial activity. Biochar maintained high DO at 8.09 mg per liter.
But in the final combined stage, DO dropped to 6.45 mg per liter. This may have been due to the decay of algae which fed any bacteria present, consuming more oxygen. Although the combined stage has a data point that significantly differs from our hypothesis, the individual treatments prove that the experiment works, but further research and improvement must be made.
The next testing is ICP-OES, the results of calcium, magnesium, and copper concentrations in 5 water samples, including drinking water and variously filtered lake waters. First, raw lake water showed high calcium and moderate magnesium concentrations, resulting in moderately hard water. In contrast, drinking water had very low levels of both, classifying it as very soft. When we filtered the lake water using algae, calcium was significantly reduced, slightly lowering the hardness to a slightly hard level. This suggests that algae are effective at softening water by absorbing or precipitating calcium.
However, filtration with biochar caused a sharp increase in both calcium and especially magnesium. This raised the water hardness to a hard level, likely due to ion release from the biochar surface. When both algae and biochar were applied sequentially, calcium remained low but magnesium stayed high, resulting in similar water hardness to the raw lake water, but now with a magnesium-dominant composition.
Interestingly, copper levels slightly increased after treatment, especially in the combined filter. This could be due to the leaching from algae or biochar. In conclusion, algae help soften water while biochar may increase hardness. So understanding the behavior of these materials is crucial when designing filtration systems.
In conclusion, our study on purifying lake water using microalgae and biochar highlighted the unique roles each material plays. Microalgae proved effective in reducing calcium levels, softening the water, and showing healthy growth throughout the cultivation.
On the other hand, while biochar has potential in water filtration, its tendency to release ions like calcium and magnesium can increase water hardness if not properly treated. Together, these findings emphasize the importance of understanding material behavior when designing a sustainable and efficient water purification systems.
That's all from us. Thank you for watching.